how to do these problems with pure fluids. So we have two people here kindly consented to work out the problems. Not all, just a couple of examples, maybe one or two. Chase will do it on the PC using the book software, and Kevin here has brought his Mac to do on pure fluids. I want you to pay attention for you guys in pure fluids. If you have any questions, this is the time to ask. The pure fluid software, as you will see, is fairly straightforward and very easy to use, but all the same, you still need to know what you're looking for, okay? And now, where's my book?
That's yours?
Yeah, that is mine. And you took my stuff out of it.
Chase did.
Huh?
I saw him going through a book, but I think that's
did you
his.
take your book or my book?
My book. That's your book.
No.
I didn't
My
touch
book's
it.
got my paper in it.
Yeah.
I didn't touch it.
Okay, so what we're going to do is work out the problem that was given on the exam, okay, using the software.
Or do something simple.
Or something else. And I am again asking you in several different ways, coded, uncoded, be prepared to use the software. Okay? We will be working this, we'll be giving problems out in such a way that every student will have a different problem. I mean, at least different numbers. Okay? But that's okay.
All right, give me a minute.
There will be no class on Thursday. There will be no class. Huh? Oh! There will be a special class only for those who have to apply.
Nice.
I still have 14.
We have nothing tomorrow, right?
It's worth skipping.
I mean, we did take an exam today, so we can go over.
I understand that's a great present. Well, when you can either give me back a present, or I'll be more than happy to extend it. We'll pass out the hat. Okay. And you can put candy, you can put rubber paper in it.
Words of encouragement.
Huh?
You need another president.
Oh, you have another, no, you don't have. Yeah, you have me. I'll be there next Tuesday. Give me the full class. That's your present, right?
Oh, yeah, the Tuesday after. That's really good. All right.
Okay, go
All
ahead.
right. So, guys, we're going to do a little bit different version of the problem 1 from exam 2. We're going to use the vapor compression cycle. The only difference is, or the main difference is I'm going to be using water, just because I have water in the compounds list. It's a lot easier to use. So what we're given is I put all the givens over here, and I gave some information that you have to know, that is, should be known to you. So for the first spot, which is over there, we have that it's given to us at 55 degrees C, and that it's a saturated liquid. Okay, we also are given a temperature for 5 degrees C, and a saturated vapor. Now on the exam, it was a different conditions. They weren't saturated, but this is the way I'm doing this just for example's sake. We also know from 2 and 4 that the process between 1 and 2 and 2 and 3 have certain rules. So we know that that it's isobaric from 2 to 3, so our pressures are the same. We know that it's isenthalpic from 1 to 2, so our enthalpies are the same. We know that 3 to 4, we have isotropic, so our entropies are the same. And we know that 4 to 1 is also isobaric, so our pressures are the same. So does everybody follow that? That's the given information we're going to need, and then everything else we can just do from the program. So, where do you guys want to start? Where do you think is the best point? 1, 2, 3, or 4 to start from? Anybody? 2, 1, 3, 4, no? Nobody?
1 to 2.
1 to 2? All right, why don't we just start defining number 1? So we know number 1 is at 328 Kelvin. We know it's a saturated liquid. So to find this information, we're going to have to go in here. I already loaded up water. Okay. So we're going to go in here. Problem is, we know it's a saturated liquid, but we don't know the pressure. So we can't find our equation state information without the pressure. So to find our pressure, we have to go in here. We're going to make this 250. We're going to make it go to 400. We're going to make it change by 2s. We're going to plot our pressure temperature. So it gives us our plot. So we can find that 1 over temperature for 0.1, the first position here, was 0.031. So we're roughly about right here. Okay? So if you go up, since it's saturated, all right, we said it's a saturated vapor or liquid, it means we're going to lie on this curve, on that line. That's our equilibrium point. So we go up there, we come across, if you do it, this is where reading your graph, you can get off by a little bit, it'll make a big difference. When I read it, I got to about 0.15 bar. So if you read off that, you can get out that your pressure should be about 0.15 bar.
Is it possible, if we make a guess, that we can refine the graph by going in smaller increments in that region?
You probably could to make it better. You could probably try and refine it to get a
I mean,
better
I'm just
one.
asking them like I want.
I'm not sure, because we found that once you get to a certain region, remember guys, it just
Yeah.
goes to crap. So just get your best guess. We'll be nice with the assumptions, but hopefully we'll see how it goes. But so you get 0.15 bar. So from this, we can now find our H value. We just go back to our program. We know we're at 0.15 bar. We know we're at 328 Kelvin. Calculate equation state, spits out information.
You put 3,288.
Oh, I did. All right. Well, let me fix that. So that should give us this number for the. Why is it all? Okay, I got a different number on that pledge. Oh no, there it is. All right, negative 43,297. I think it's point something, but it doesn't really matter. Joules per mole. All right, so we have our enthalpies. So now we have our first spot defined. And we get S as well if we want. S is negative 115.51. All right, so we got, now that's position 1. So for 2, now we can get part of information for 2. We know H is H1. So we know that H here is negative 43297 joules per mole. So we got that number. But we can't find P yet. We also don't know what T it's at. But so we gotta leave this alone for now. 0.3, we know that it's at 278 Kelvin, it's saturated vapor. So we're gonna go back to the graph again, do our same.
Do I understand that you don't know P at 2?
You don't know.
T I understand. But
You know T.
But you know at 0.2.
At 0.2, you know P1 and P here is equal to P3. So you could
Okay.
get back out if you just wanted to.
I see. Got it.
But we're gonna just get P here and we'll know P there.
I see.
So we know 3, we got 278 Kelvin saturated vapor. So go back through our graph once again. So here, once again, we can look at our temperature, which this time is I think it's 00351, somewhere in there. So it's down over this direction. If you read it off, you'll get a pressure of I got 0.009 bar. So you can use that, you get that P. Yeah, you can make it 0.0, it actually makes a difference. But you can get 0.01, 0.09, you'll be in the general realm.
Wait, how do you get this? Okay,
Yeah, just go ahead.
All right.
I mean, ask the question.
Yeah.
okay, so I'm confused because you need the temperature to be 278, right? So you put it in like the,
So I did a range
like,
of
So he drew a graph, he drew a
250 to 400. So here I did a range of 250 Kelvin to 400 Kelvin.
and then so you find like 1/278.
Yeah,
Right.
which turns out to be somewhere like right here. It's like
And then-
0.0035.
Okay.
And because it's saturated vapor, you're on the same thing as saturated liquid. You're on this curve.
Yeah.
So you go up to the line, then go over to your pressure, and it turns out to be about like right there,
Okay,
0.009.
and it's because it's on the line because it's saturated.
Yes.
Okay.
Saturated is, right at the equilibrium point. You could go one way or the other by just a little bit of a change. So that's how we get our pressure. From this now we can go back, once again, put in our new pressure and our temperature. Here, close this.
It's always good to, just from my own past experience, to try a few of these because
Yeah.
it never works the way you always think it's going to work. And so, let's just try it out.
Yeah.
But it will.
Alright, so yeah, so this is the right thing. So now we know we can find our enthalpy and entropy here for 3. So we got negative 677.6 or 7 and 36.8. So this gives us that H is negative 677.7 and S is 36.31. So now we've got that. We also know up here P is 0.009 bar. Because it's the same as this one. Turns out, find out later that doesn't matter, but so now we know S here, which means we know S here. We also know P here. We know P is equal to P1. So this is P is 0.15 bar. We know that S is 36.31. So now we got to find out what's the temperature and enthalpy here. Well, to do that, now we get to do our good old guess and check. We know the pressure is 0.15 bar. And then we got to put in temperature and see if we can get, we want to get it to where our, in this conditions, we want it to equal 36.31. Right? So, we're going to do, let's start with, so the other thing is I labeled it over here, it's superheated vapor in these conditions. So we're going to go up to 400 Kelvin, check that. We see that at the vapor we're only at 25.76, so we're going to keep going up. 500.
That's, we found
36.55, still not there. Alright, so I'm just going to skip ahead, just say that it's actually around 540. So you see at 540 we're at 36.29. That's close enough, right? So now we can read off that our enthalpy is 8377. Also our T is 540 Kelvin. And H is 8377, right? Yep. So 8377. So now we have all our enthalpy, right? So what we were looking for before, I'll put it, so I'm just going to put it right here. We know that we're looking for COP, which is Q over W. It's actually one of these Q's. So we're looking for H3. Yeah. Looking for H3 minus H2 over H4 minus H3. So we have all these numbers, we plug them all in. Can't right now, I don't have enough space, but you should get around 4.71. And that'll be your final coefficient of performance. Did anybody have questions on how I got to all of that? I know it's kind of quick and I kind of just, what, have questions on anything? Yeah.
Finding the equations for Q and W is another thing, right?
Yeah, well, Q and W, we say it's the delta H across the where the pieces were.
Okay.
So we're looking for the work here. We're looking for the Q here. So we know it's H final minus H initial and H final minus H initial. But yeah, that's
At part 2, did you find the temperature at that part?
here.
Yeah, could you use the program to find it there, since it's mixed?
So to find it, you could get it back out what the temperature is. You'd have to do a little bit of fancy work to get it, but you could get it. You'd have to go back, use the whole X, X times.
Okay.
Because it's constant, what, enthalpy?
So,
Yes.
Yeah, constant enthalpy, so you'd have to do that X, H vapor.
so at every guess, you need to use that equation to see if it's the right guess? That's what you're saying?
You'd only need to use that if you wanted to get back out temperature. We knew it's isenthalpic, so we knew that the H of this mixture had to be H here.
Yeah, no matter what.
It doesn't matter what the mixture is.
Okay.
Now, if you want to get back out other pieces of information, where you'd have to have, you might have to find the mix, what the actual mixture composition is.
Yeah.
Luckily, it doesn't matter here. You only need to find the H for this question.
Okay.
Anybody else?
Can you do it in Mac?
He's got math. I don't know what problem you're doing.
I can do the same problem.
I mean, if you want, it's the same process.
Up to you.
Yeah, we
Yeah,
like to do
I
that.
don't follow.
Well, we'll do a few, maybe.
Yeah, I mean,
We'll do a few steps.
Yeah.
I think we'll keep this here.
Yeah, I'll leave it.
I want you
leave
to
that
know
here.
one thing. The H's are not gonna be the same neither are the S's, right? Because the reference dates used
Yeah.
in every program will be different, but you know that. It's the delta H's which are important, okay?
There it goes.
Yep.
Oh, so the first step here is to open up pure fluids. I'm gonna make it big so you guys can see it. Okay, so pure fluids is actually a little bit easier interface to use than this PC thing. So the first thing that you need to do is pick your fluid. So I think we use water, right?
Yeah, you should have
Okay,
water.
so I'm just gonna go down and pick water. And pure fluids also gives you the option to pick your equation of state. I always pick the one with the star beside it because I think that one is like what's known to be the most accurate for this, whatever compound you've selected. But your answers are going to be similar no matter which equation of state that you use. So once you pick that, then we can proceed on with the same steps as before. So I think when Chase did this, you did part 1 first, right? Number 1. So number 1 says it's 328 Kelvin. It's a saturated liquid.
Yeah.
Okay, so what you want to do on pure fluids for saturated things, liquids or vapors, you click this tab right here at the top. It says saturation. Click that. Sorry, you are going to have to put your fluids in again. So water and your equation of state. We know that the saturation, that this water is at 328 Kelvin. So I'm going to go 328 Kelvin. That's the only number I actually care about, so I'm just going to put it 328 to 328 and hit add new saturation table right here. Okay, well, maybe I need to put. Okay, you need to put an increment too. It doesn't matter what you put. And then click add new saturation table. When you do that, you'll have a list of saturation conditions up here on your right. Your next step is to click down here at the bottom right corner, click calculate. Once you click calculate, you go to the report tab in the top. And this report tab will tell you here the liquid, and another good thing about pure fluids is you can change the units where you're stuck on this PC thing. So I'm going to change the pressure to bar so that we don't have to send a bunch of stuff. So pressure in bar, so now I have a saturated liquid at 328 Kelvin. This tells me that's at 0.156 bar. That's pretty close to what Chase read off the plot, but I would claim that mine's probably more accurate because I didn't have to read it off a chart. And